Absolutely seamless. Hopefully, we should now be online. Everyone should be able to hear us. So firstly, thank you for everyone for attending. We've got a good few number of people, 10, 15 online now. We've got quite a good audience for tonight. So I'm here representing the HVAC committee. Effectively, I'm the vice chair. We meet on a regular occasion. We trying to change slides to make sure I'm really trying to be professional. It's honestly seamless. You'd never know any difference. So just, you know, if you actually want to follow us actually through LinkedIn or through the website, here's some points here to go from. And if you actually want to sign up actually through the website itself, you can actually go through CIBSE.org, click through actually for the special interest groups, or you can click and follow us actually through LinkedIn, going for that way as well. What we want to try and talk through tonight is critical systems. Most people associate that actually with comms rooms and server rooms, those bits and pieces. We want to talk about some actual proper critical systems, not just some stuff actually sitting on Facebook. We've got two fantastic speakers here tonight talking around the range of different subjects. If we could try and hold back the Q&As, both online and actually in person, to the end, maybe actually they're going to cause a bit of a question mark between themselves, how it's going to go from. But first of all, I'm going to hand over to Cole from DEFRA, and if Cole, you actually want to use the clicker, we go for that way. And looking forward to hear a fantastic subject.
Great, thank you.
Thank you.
Thank you, everyone, for having me to present today. So hopefully you've seen my profile. My background is that I'm actually a chartered engineer that specialised in the healthcare and laboratories, working for DEFRA, looking after the design authority. They've got their really intelligent client function for looking at requirements. So the subject I really wanted to talk about today was about the critical systems and ventilation related to containment suites, but really about the concept of One Health. And what I'm trying to do is introduce the One Health concept to engineering. So today we've actually got a presentation with the CIBSE group here. It's really to promote discussions that we're going to have around engineering awareness, what we're trying to do for specialist facilities. And the One Health approach really is sort of implementing research where we've got multiple sectors actually working together, sort of coalescing together to try and get better health outcomes. And it's been utilised to address health threats, both in the animal and human and environmental sphere. This research is currently expanding in the UK and around the world. I'm going to show some demonstrations on this. And this presentation that I'm going to go through is intended to cover a high-level element of the subject, just so people are aware of what's coming up. So in terms of the content of what we're going to look at, I'm going to just try to touch on what One Health is. Then sort of a new way of strategic paradigms for resilience, the way things are going. The threat classifications that we've got in terms of pathogens and diseases. Then I'm going to talk a bit about the design requirements related to the different containment levels of facilities. Then I'm going to talk about the high-level containment facilities, energy use, and the elements on sustainability. Okay, so we're going to start off with One Health. So One Health, as it says there, basically it's an approach to designing and implementing programs, policies, legislation, research, which multiple sectors actually come together to achieve better health outcomes. The One Health approach is critical in addressing health threats, as I've said before, in the animal, health, human and environmental interface. And there was a purpose for this, and there was a need to change, because what they were finding that by working in silos, they were not getting the best in terms of solutions. You know, the need for change was really to find sustainable solutions, really to present, you know, social changes and looking at the threats that were coming through infectious diseases related to climate change. Whilst it's an emerging paradigm, it's not new. It has been around for a while. It was identified as in the 19th century, where they were talking about one medicine, one world health approach. There has been a resurgence with this in the Manhattan Principles when the SARS outbreak took place. It gained a bit of momentum, surprisingly, once we had the COVID outbreaks. And then really since then, what we've actually had is the One Health has been pushed forward by the United Nations. They've got a 5-year plan that started last year. And we've got a United Nations are now looking at UN Sustainable Development Goals associated with it. So it's something people do need to be aware of, but this is what's coming down the tracks. So what we've seen really is that we believe this is a growing field. It's been steadily growing for the last 7 or 8 years. As I've said, the most significant changes have really been observed in the last 5 years since the COVID issues. And the big data really does help with the look at the data, the volumes, and how it's all processed. And I'll just talk a little bit more about this as we go forwards. So there is a rationale behind this, and you can see the map there showing the overset and the overlap between the human health, environmental health, and animal health. Of course, for us, the environment itself is that basically, you know, if the ecosystem works, provides us with our food, fresh water, and regulating climates, you know, disease control and recreational benefits from the environmental side. We're very concerned, of course, with food safety, particularly at DEFRA. Unsafe food is an issue, and you know, as this shows, there's some statistics showing that World Health Organization estimated that many thousands, hundreds of thousands of people have actually died from unsafe foods. Zoonotic diseases, that's where we're starting to talk about the sort of bacteria, parasites leading to infection, or naturally transmissible from vertebrates, animals to humans. That's where we're really starting to see issues. This can be spread through direct contact with foods, as well as water and other elements of the environment. So the approach has been that there's been some changes in terms of strategic level of thinking. And what we're seeing is that planning across disciplines, barriers are broken down. So the human health, doctors, nurses, practitioners are working more closely with the animal health vets and agricultural workers who are working with ecology and wildlife experts in the environment. And we're also getting people in the mathematics world and modelling, working through looking at the elements and issues. We're also seeing now strategic planning across borders. Governments themselves are starting to work with communities, and they're starting to work with other initiatives from international concepts. So we're starting to see the shift in what's happening with the way people used to work. And what that means from an investment point of view, from the UK in particular, we're seeing that the UK government is actually maintaining a high level of research, pumping money into research. The Home Office are undertaking works. The Department of Health and Social Security are undertaking works related to this. DEFRA undertaking works associated with this. And the Department of Business, Energy and Ministry of Defence are also taking note of this and looking at this as a concept. So what does it actually mean in terms of the paradigm shift? What's actually changing? We are actually seeing UK policy changing, where we're seeing a One Health approach impacting on the climate change and the public health, and that came out only this year. That's how recent it is. That's associated with the next item that's on there, the Global Health Framework, working together towards a healthier world. Again, that has been published again this year. So it's all fairly recent. And we're starting to see it in the finance area, because the government, HM government, is starting to look at green finance and strategy deals, which are now starting to include environmental, social, and governance elements. So it's all starting to shift as a sort of coalescent way of thinking. But what does that mean for us in terms of us in the built environment? What it actually means is that there's going to be new facilities or extensions of existing facilities, so we can have interdisciplinary science studies taking place. And that's really the key element. So what we're seeing is an expansion of new facilities for, as I said, interdisciplinary science, where we're really start to research into the biological threats themselves. And those threats could be natural, accidental, or deliberately released into the environment. That's what we're trying to look at. Whereas that can got a potential to endanger lives or to disrupt economies. So that's the sort of elements that we're trying to focus on. In order for them to do that research, there's a requirement for high containment facilities, which actually allows us to proactively look at these facilities to handle the bioagents that could actually cause serious harm. So that's effectively the way the steps are, and that's how we're getting to where we are. The key thing is that the UK is not alone in looking at this. You know, the UK is there pushing at this, but within the last few years, a whole host of nations are starting to look at developing facilities like this. So they've actually got their own national capabilities to start looking at bio threats. So when we start talking about bio threats, we really need to start talking about containment. So I'm just going to go through some very high level elements. These are some foundation elements. So containment laboratories, you know, the main function there is that they're built to, you know, preserve, to prevent the control exposure of laboratory workers, to make sure they're not harmed, protecting other people in the environment, and to the biological agents that are in use, and containing those. Biological agents themselves are actually identified in COSH. Most of you probably know what COSH is. And they're actually regulated by the Advisory Commission on Dangerous Pathogens. Some of you may be familiar with that, who have actually got different hazard groups with different biocontainment elements themselves. And those are split into 4 groups. Groups are often referred to as biological safety levels, BSLs, or containment levels. So where we've got bacteria, viruses, fungus, and genetically modified organisms that can actually cause disease, known as the pathogens, these are actually split into the 4 groups, depending on their hazards. So when you start to talk about working with outside of science and into animals, again, there's also classifications of animal groups as well. And they go from groups, and you go from groups to 2 to 4, with 4 being the highest risk, just as it would be in the sort of advisory committee of dangerous pathogens. The control of the animal work is actually via DEFRA itself, under the specific animals pathogens order itself. If you're actually doing work with animals, which are live animals, you've actually got to work with the Animal Specific Scientific Procedures Act, which means that you will have to get involved with the Home Office itself and their inspectorates. They have to be involved in the projects because they're looking after the welfare of these animals and conditions of it they're contained and kept. We also put a note there about genetically modified organisms. They're categorised under genetically modified organisms containment use, again, for controlling what work you can do with those organisms. So really, when we're just talking about control of contaminants, there's sort of 3 areas that I've identified. If we're talking about human diseases, it's the Advisory Committee of Dangerous Pathogens, really looking at that, and they're regulated by the HSE. If you're looking at animal diseases, then it's the specific animal pathogen order, or SAPO regulations, and most people know that. And I mentioned previously that is regulated by DEFRA. And zoonotic diseases, where there's a transfer from animals to humans, is a combination of the 2. So I've just listed here, I'm going to go through this very quickly, with the groups. So a group 1 pathogen is unlikely to cause you any real human harm. Group 2 can cause some harm, maybe a hazard to employees, could spread to the community, but usually there is an effective treatment available for that. A group 3 pathogen will cause severe human diseases and will be serious hazards to employees. And if it spreads to the community, it will be an issue. But then again, there generally is a treatment available. Group 4, unfortunately, causes severe human disease and serious hazards to employees, and likely to spread to the community where there is actually effectively no treatment. So that's the elements we've got to make sure we contain. Likewise, with the SAPO elements related to animals, similar sort of grouping. disease-producing organisms for group 1, where it's an enzoonotic available. It doesn't really produce any notifiable diseases. Group 2, disease produces organisms that are either exotic or produce notifiable disease but have a low risk to spread from the laboratory. Group 3, very similar, have a moderate risk of spreading from the laboratory. And again, a group 4, where we've got a notifiable disease that's a high risk of spread from the laboratory, and again, where there's generally no raw treatment, i.e. where we've had some of you might remember the foot and mouth disease outbreak that we had a number of years ago, or outbreaks or rabies, which would be classified within that group. What I've just included here really was just more for reference, was just about microbiological containments and legislation. That's the legislation that works with the COSH and Health and Safety at Work Act, so that you can just at least see the guidance of where that comes from, the primary, secondary regulations, you've got guidance. And what I've included on the right-hand side is really just a reference guide, so people can at least see the major steps required for containment measures. When we start to talk about pathogens, there are in fact different pathways by which they can actually spread and invade to a host, different routes. And I've identified airborne transmission, those very small droplets, less than 5 microns, and they stay in the air for a very long period of time. We've got droplets, which are much bigger, generally wet particles, larger, and they're only in the air for a very short period of time. We've got direct contact from an infected individual, and an indirect physical contact from touching the surface, and then you've got fecal or oral transmissions. When we start to talk about the high containment, we're really going to be focused very much more on the airborne transmissions. When we start to talk about high containment labs, we're really trying to focus on biosafety. And biosafety for us is a laboratory that's described as having the containment principles, technologies and practices that are implemented to prevent the unintended exposure of the agent and toxins or accidental release. So the basic function of a containment facility is to provide a safe method for managing the hazardous chemicals themselves, where health and safety is the dominant concerns. And we've actually got 3 different methods by which we can actually contain this. We've got the laboratory operating procedures from the research staff themselves. We've got safety equipment, and we've got the facility physical designs. As engineers, we've actually got a remit to really look at the last 2, the safety equipment and the physical designs themselves. And I'm just going to go through a few elements related to that. When we talk about safety equipment, the first thing that there should be in laboratories is the primary containment barrier. I'm not sure if people are all familiar with safety cabinets and microbiological safety cabinets. That is the sort of the main instrument by which work can be done, and it separates the worker from the actual space itself. This is just a diagram to show how that works. I'm going to go through just to show that, in fact, there were 3 classes of safety cabinets. There's a class 1, which is a sort of a low to moderate risk work that you're undertaking. It protects the personnel only. It doesn't protect the product itself. I'm using that type of facilities. Probably the most common type is the class 2, which protects the person, the environment, and the product itself. And it actually has to go through a series of HEPA filters to make sure we've got a airflow that controls where the pathogens can actually go. This is utilising the extract air is 100%, so it should be taken externally, and no air should be recirculated into space. And then we go to the class 3, which is basically a box which is sealed completely from the environment itself. So it protects the person, the product, and it's basically airtight construction. So you've got to manipulate it by working in there with your gloves. And if people want to put a product in there, they've got to go for a pass-through hatch to get it in. So what we spoke about was the primary containment. So people should be doing their work within that primary containment. There is, in fact, a secondary containment, which is, in fact, designed the facility itself. And that's basically the external boundary of the lab envelope. really to contain the actual aerosols, pathogens, really to make sure that's not within the primary containment device, and really to make sure there's no breach or leakage of the biocontainment to the external environment. That's its main function. As mentioned there, the secondary containment is a combination of operating procedures. That's those that are actually working within the space, and the way that handle the biocontainment, pathogens, its safe disposal, and about the design of the laboratory engineering systems, particularly the engineering ventilation systems. So the actual laboratory room itself is considered to be the secondary containment barrier. I mean, what we want is inward airflow into that space. And by doing that, we make sure the extraction is greater, so we've always got an inward airflow to the space. I've put a note there just to say that as the potential risks of the pathogen increases, so does the actual containment facilities that we actually apply to the spaces. Just want to really just touch on some of the engineering design key points. When you actually start to look at this, you determine sort of what the hazards are through a method called a HAZOP, where you actually look at the utilisation of the built environment itself, the engineering system design concepts, and good codes of practice. Design parameters for laboratory we would generally consider the following. These are the key things that we normally look at: the biological containment provision that you've got, the equipment and the occupants, heat gains, both sensible and latent, size and number of laboratory safety containment devices, the equipment that we're utilising, minimal airflows that we would like to use, the air quality that we're trying to perceive, both for filtration and the extract systems, particularly through HEPAs. Some of the key points that we are looking at generally within the engineering are temperature and humidity controls, both looking at from inside and outside. The actual style of the exhaust devices to capture velocities, usage factors, decontamination provisions, the isolation of the room, the pressurization requirements, exhaust discharges, the intakes and outtakes, where those are actually cited, the need for standby equipment and alarm requirements. So there's quite a bit there that we've got to make sure are considered. And what I've actually done is just gone through a very high level of saying what's actually in the engineering considerations. So for safety containment level 1, you can actually do the work actually on an open top space. Bench top, it's not advisable, but you could do. Where the engineering requirements, there's no specific engineering requirements, it just should be good engineering practice. When you move up to the next level, you actually start to look at some potential for creating infectious aerosols that are conducted. So you really should be working with a safety cabinet. You should be looking at 100% outside air for the ventilation and dilution. The air change rates could typically be between 6 and 15 air changes. Directional airflow is required, so it should all be negative to the space itself. And specific phase velocity is if you've got devices such as fume covers or safety cabinets. You've got to make sure those are correct, otherwise they don't function. When you start to get to containment level 3, why the reason elements are in blue are these additional elements that are really added on top of containment level 2. So we've got to make sure we've got things like alarms there for monitoring, gas type dampers in the supplies, so that we can actually decontaminate the labs themselves. We're actually looking at fumigations for decontamination. Penetrations to the safety labs have actually got to be sealed really for gaseous decontamination work, gaseous decontamination work. All the procedures should be done within the safety cabinets, and exhaust from the safety cabinets and the air should go through high efficiency particulate filters, HEPA filters. When you get into containment level 4, again, we're just adding on even more. So the ventilation system really here should be dedicated to the laboratory and shouldn't be integrated with any other part of the buildings. The supplies should be filtered as well, so we've got HEPA on the supply as well as on the extracts. There should be a minimum negative pressure within the space compared to outside environments, identified 75. When you're actually extracting them from the labs, you should in fact go through 2 HEPAs, and they should be mounted in series before they leave the labs. and they should be able to be independently tested, and they should be in safe chained houses. So you can have to test them and look at them for fumigation. When we actually look at the extract system, that should be as far away from the space as you can to make sure all of the system itself is under negative pressure. So this extract is far away to as close as you can get it to discharge points, so that everything's under negative pressure. And there should be sufficient redundancy built into the air systems really to provide a backup for allowing workers to be able to exit the labs should there be a problem, really allowing them time to shut down experiments and decontaminate before they leave the area, which would allow for also backup power generations to allow for that to take place. The animal procedures are very, very similar. Again, I've mentioned about the SAPO requirements. And again, this really talks about the fact that you've got to work with the Home Office to make sure that those procedures are correct. And not surprisingly, the requirements, again, I've heard is similar. So a level 2, the room should be mechanically ventilated. It's got to maintain an air pressure, negative to environment, with a good flow of air to the room. It should be adequately ventilated, and there should be good temperature and humidity control. When you step up to level 3, for animal rooms, again, the air should be extracted through HEPA filters. Again, comfort for both the animals and staff. Ventilation system incorporate means of preventing reverse flows. Connection should be interlocked again when you've got containment free, really to prevent the room going into positive pressure. So it's got to make sure if the extract fails, the supply should go off as well. Containment level 4, the next level up, very similar to what we had on the ACDB 4. Double HEPA filters, negative pressure to the space, being -70 pascals, difference between the zones between them, and there should be power failures, standby provisions. High containment areas, in fact, have a couple of specialist elements of equipment. One of those is an autoclave, and that's basically a chamber for sterilising decontaminated waste with steam under pressure. You can see these in hospitals in other areas. They're generally quite small. When you're working with containment facilities, they can be very large because you've got to get large elements of kits in there, such as cage racks and other elements. And the other elements that's quite specialist to high containment facilities is the effluent treatment plants. Not to be confused with the effluent treatment plant that we have in the water industry, where a lot of that is about filters and filtration about the actual particle size. This is really for decontaminating waste so that it can be discharged into the general sewers, and you may have to use heat treatments, chemical treatments to neutralize it before you can actually do that. Quite complex, and these are generally sat below laboratory levels. So they work by gravity. So where you've got your laboratory level, you generally have a basement or a lower level, so this equipment can be placed. So it takes up quite a lot of space for those sort of facilities. There's a whole host of things that we would need to consider under engineering that we can't go into today because we've got time, and that would include things such as functional safety, the commissioning of systems, secondary containment barriers and decontamination and how you fumigate for those spaces, sealability of those areas. A big issue for high containment facilities is biosecurity. Some of the toxins that people are working on could become a threat otherwise, so the security of that is an issue. We've got operating and maintenance elements, and of course now we've got to start thinking about sustainability. I've just kept in there a guide, just a sort of summary guide, some of the things I've been talking about, really just a sort of quick aid memoir, and that comes from the World Health Organizations, who've done as well a quite a neat little overview table. So it's just a reference. I did mention sustainability because containment labs themselves are extremely high in terms of the energy use and energy use intensities, and that's really due to the fact that we've got a lot of full outside air changes going through the space, and it all needs to be conditioned. in terms of determining some of the energy use for sort of the facilities we're talking about, I'll put the energy use intensity value of 800 to 1,000 kilowatt hours per meter squared per year, which is extremely high, much higher than hospitals. There is some work going on. I'm not sure people are aware with the UK net zero carbon building standards, and they're looking at also other labs to see what those values are. But that's the sort of average value that we're getting for this sort of facilities. Steam is used quite a lot in autoclaves because you can actually destroy the microorganisms and the pathogens, because the moist heat actually denatures them and breaks, goes through the cell wall barriers and kills them. So you tend to find a lot of these facilities got steam networks on the sites. And that steam network would supply not just an autoclave, you can do humidification, could also do the thermal heating as well. One of the things that steam boilers have generally been used for is that fuel supply has generally been gas or gas oil, which is becoming a bit of a no-no going forwards in terms of sustainability. So the drive is through the government and other elements with the net zero is that we're going to switch really from fossil fuels to decarbonised electrical supplies, which is all well and fine, and you know. But it does mean that we have to start looking at things such as heat pump technologies, because if you just go to direct electrical steam boilers, which we've been looking at some very large scale, whilst they can do this and they're quite energy efficient, the cost of the fuel is 3 or 4 times that of gas. So suddenly your running costs skyrocket if you try to go in that regime. So what we're having to start to look at, because we're starting to do some work on large scale steam generations, is we're starting to go to industry and start to look at steam generations from heat pumps on a much bigger scale than has been done from what you'd normally see on the commercial market.
I'll actually show an example.
Oh, brilliant. Oh, look at
In
that.
the pharmaceutical industry.
Brilliant. There you go. And I was just going to say, industry is looking at that, and we're going to have an example directly after this. So this was quite a quick canter through the areas. What I really want to do is a bit of reflection on the critical systems and the sort of presentation itself. One of the key things I wanted to really introduce was really about the One Health, and that the One Health is a paradigm shift to how health is going to be reviewed, and that's really establishing a critical integrated research. That's what's taking place about threats to food security and other elements. That then leads us into the containment laboratories themselves, and I've done a very quick canter through, but about critical engineering systems, and there's quite a lot. There's a lot there in terms of guidance, and it is quite a deep subject. But it's really about maintain biosafety. Those are what the critical systems do. They maintain biosafety, the operators, and making sure that we don't have an outbreak. But now we're having to pick and balls in terms of critical system sustainability. And what do we need as power, in fact, to serve all these critical systems with critical engineering? And I really just wanted to leave you with a sort of a comment, really. I believe that there's a sort of a growing need for built engineering, environmental engineers to have the knowledge about the One Health growth. And that's why I'm doing these presentations, and really about the field of scientific investigations in healthcare and product developments, where high containment facilities, I believe, play a critical role in preventing, detecting, and responding promptly and effectively to the threat of global health security. And that's where I'd like to leave it.
Oh, that was really quite interesting, actually. I should say, actually, I tried all the event. Don't want to sell the whole there, but I think it almost underlines almost a knowledge gap. That to a degree, the fact that you've got people here, I know from a varied background, that are already quite more understanding over the considerations. Actually, what you've got around, what we've got to go for, and hopefully there'll be some great questions that come out afterwards. We've now got Gordon. Almost sounds like he's going to tell us all the answers, which I'm looking forward to as he's coming through with me here. So Gordon's lucky; he's got a nice clicker. But if you wouldn't mind, just making sure you get close enough to that.
Okay, I hope
they
can hear. So Carl has actually sown the seed. We're completely unrehearsed on this, Carl, but it fits perfectly. So I'm going to focus on the clean bit mostly, Carl focused on keeping nasty things in, and I'll be talking mostly about keeping nasty things out. However, particularly in the biological sciences, these two are often close together. So who's heard of Botox? So Botox is produced as a therapeutic product in surgery, particularly eye surgery, to paralyze the eye, for example. It's also used cosmetically. Where does Botox come from? It comes from the fermentation of botulinum, which is a human level 3 pathogen, slightly modified to express the toxin. The toxin is separated from the bug. The bug's killed, as Carl just said, in a bio-waste system and thrown away. And the toxin is separated, and that is a potent medicinal compound. It's no longer biologically active. That's where Botox comes from. If we were to go across the road to Crick Institute, some of you walk past that on the way here. Down in the basement, they've got lots of level 3 laboratories, and they're handling pathogenic organisms, modifying them to make medicines. One of the things they do are viral vectors. So they're modifying things like HIV virus to make it benign to the patient, and then they use it as a carrier to target specific biological therapeutics to particular organs. And this is in fact, if you look in the biologics world, there's a huge explosion in relatively small scale biologics actually moving to individual patient medicines. So often we'll see the containment of hazardous agents and then the processing to make a medicinal product all linked together. Okay, so I was asked to talk about clean rooms. Most of my experience has been in the life science sector. So I've been working in that for more than 40 years in design, engineering, and full project delivery. I've also been lucky to be very involved in standards, starting off with British standards. So I actually was involved in writing BS 5295, 1976 for biosafety cabinets, and also a whole lot of clean room standards. And I'll mention a few of those. And I'm a chartered engineer, CIBSE member. Okay, so what am I going to talk about? What is a clean room? So I'm going to characterize what we mean by a clean room. Clean rooms in the life science sector. So I particularly want to embody the regulations, and these are good manufacturing practice regulations. So it's a bit like the SAPO and the ACDP that you've heard about. There are regulations, and we have a responsibility to engineer a solution that meets the objective of those regulations. So if you're in the facility manufacturing medicines, you need to be aware of these good manufacturing practice regulations because they prescribe some of the performance requirements of the space. Clean room technology also includes devices like restricted barrier systems and isolators. I'll show you some pictures. So it's a bit like safety cabinets, but again, mostly for keeping nasty stuff out rather than keeping nasty stuff in. But the engineering of these things is virtually the same. They use pressure differences, they use HEPA filters and so on. We talk very much about quality, critical quality attributes of the space. So my space has to have certain performance requirements. But the system, particularly if you think about HVAC or other critical utilities, that must perform in a certain way to deliver those clean conditions. So we're always talking about the conditions in the space, which are defined mostly in the regulations. And then as engineers, we're having to engineer a system that works to deliver those conditions. Same in the containment world. So you'll find that the discipline and the thinking here is exactly the same. There will be some different language used. So in the life science sector, I call it beyond commissioning. We have things called qualification and process validation. and I'll talk about how those are linked together very briefly. And then we have an ongoing real-time monitoring. So we need to monitor those critical attributes of the space to provide evidence on a continuous basis that the space is right. So it's not just temperature and humidity, it could be pressure difference, it could be air cleanliness by particles, it could be microbiological cleanliness, and so on. Then we have some sustainability and energy considerations and system optimization, and I'll talk about some examples of that. And if there's time, we can have a chat. Okay, so what is a clean room? So that's what a clean room looks like. It is an enclosed space in which we try and deliver a whole range of performance attributes, critical quality attributes. Now, number one for a clean room is that the cleanliness of the space is first defined by the total concentration of airborne particles. That's particles per cubic meter, and we classify the room by a classification system that describes the number concentration of particles. So before I can call it a clean room, I have to have designed it and tested it to demonstrate that it meets this cleanliness requirement. And there are things all the time that are trying to invade that environment. External contamination, contamination sources internally from people and process and so on. So I need to understand those external threats and the internal threats in order to engineer the system to deliver that cleanliness. Primary cleanliness attributes are defined in BSEN ISO standards 14644 Part 1. There is a whole family of standards. I'm not going to go into detail of all of them, but be aware of it. Now, the UK has been heavily involved in writing standards like that since the first British standard 5295, going back to the late 70s and early 80s. But now you will find UK experts actively involved in all these CEN and ISO committees. So the UK has a major contribution in clean room technology standardization. So primary cleanliness defined by that. Then I could call it a clean room. But I might have other attributes that are really important. So people emit contamination into the space. So, for example, we might have surface and airborne microbial cleanliness. And there's another standard, a BSEN 14171, that specifically relates to microbiological cleanliness in the enclosed space. Then some processes additionally need to have information about surface cleanliness. And there's two standards related to surface particle contamination, Part 9 of this family and Part 17. Again, UK has been heavily involved in all that work. So it's a method of determining and measuring either the particle concentration on the surface or measuring their deposition. Some industries, micromechanical, optics, microchip, are more worried about particles that deposit on their product or process than they are small particles in the air. So particle deposition is becoming the new kid on the block in a way. Okay, some industries, particularly semiconductor, are worried about particles less than 0.1 micron in diameter. So we're talking about nanoscale particles. And there's another standard, Part 12 of this family, that looks at measurement of nanoscale particles in clean rooms. I could add also surface and airborne chemical or molecular contamination. The semiconductor industry is not just worried about particles, it's worried about airborne and surface molecules that could poison the wafer that's being manufactured. Those molecules could be acid, alkali, there could be a hydrocarbon, for example. and they need to be controlled, measured and monitored. So there's another standard, 2 standards related to that. So altogether, there are more than 20 ISO clean room related standards. Some of them are cleanliness attributes and some of them are design standards, testing standards and so on. If you are involved in this game, you need to be aware of all those standards. And like all BSE and ISO standards, they're subject to systematic review. And you need to keep your finger on the pulse to make sure you're up to date. So we have a range of unwanted contaminants. So down at the small end, we've got molecular contamination, so gas molecules. Then we have small fine particles, and then larger airborne particles. And clean rooms are really working in the 0.1 micron and greater. That's when our HEPA filter starts to do some useful work. We might be in some applications interested in other particle sizes. So understanding the contaminants is pretty important. Okay, the clean room characterized by the cleanliness. Remember, number 1 attribute is the cleanliness by particle number concentration. So I've showed a picture of a human scale clean room. Now, more and more, we are putting our clean zones, making them smaller and more focused on the process rather than having big ballrooms. 2 reasons. It's easier to control the cleanliness in a small space, keeping people out. And of course, if we're shunting less air, there's less energy involved. So it might be a simple, what we call unidirectional airflow clean air hood, blowing clean air over a piece of work. And this will be sitting in a room of less cleanliness. No containment here. It might be a restricted access system. So now we're keeping people out, but we have this clean airflow, and now all the human access is via glove ports and clever techniques for transferring materials into and out of that environment. And that actually makes the room a bit less critical. We could go on the stage further to a full isolator, which can be a large scale. So there's a whole machine built into effectively a mini clean room, engineered as a composite machine and isolator, where all the manipulations are via glove ports and so on. Rather like Carl mentioned, this actually undergoes biodecontamination using a gaseous agent, not to deal with a hazardous organism, but to deal with an unwanted organism. And we use agents, same as biosafety, those agents will kill people as well. So if you're going to handle them inside that space, you have to contain that hazardous agent. Otherwise, you've got dead workers, and that's a lot of paperwork involved. Okay, these isolators can be small scale. So more and more we're seeing small scale for what we call sterility testing and advanced therapeutic medicinal products. And we want to make single patient doses inside a sterile or aseptic environment. There's more and more of this happening. Then, of course, we also have the biosafety cabinet, already been mentioned. And this is just an example of a class 2 microbiological safety cabinets. I don't advocate any vendors. Other products are available. And this is to a BSEN standard 12469. A mistake there, there's 19 too many. That's just in case of it, just to make sure you're okay. So we have another ISO standard, 14644 part 7, which talks about a separation continuum. So we could start off with an open clean room solution where we could work on an open bench, or we go right up to a closed isolator. And as we progress, we are increasing our sterility assurance, our purity, and we are increasing the separation between the inside and the outside. We're making that critical environment more resilient. So the HVAC engineer might not be designing those systems. There are specialist ventilation engineers designing these containment isolator type systems, but you would have to understand them to integrate them and engineer them into the facility, because they have an effect on the surrounding cleanliness, pressure regimes, and so on. Okay, so we then go on to other regulations. So we have the GMP, Good Manufacturing Practice Regulations. This is the UK version. We follow European regulations. So post-Brexit, we still follow those regulations. So they're called Guides to Good Manufacturing Practice, and they're tools used by industry, suppliers, as well as users of the assets, and the regulators who will audit, inspect, and license manufacturing of medicines. The regulators actually license two things: the product. So if you were making a medicine, they would review the science, clinical trials, and so on to determine that that medicine was safe. And they also license the quality. Is your factory fit for purpose for making that medicine? Both those aspects are inspected and licensed. So it's not a self-certification system. It's an audited and inspected system. There are lots of different texts covering GMP. They are pretty much the same objectives, and they're sort of 90% identical, but there are some subtle differences. So if you were working in Brazil, you would need to be aware that their regulations are a bit different in certain particular areas, the objectives of the session. The most stringent requirements in these regulatory guidelines are for the manufacture of sterile products. So those are products that are either injected or perhaps put into the eye, for example. Those products have to be sterile. Otherwise, you're going to acquire infection. That's not good news. So we need to pull these things together. So if I think about my clean room, so the quality attributes of this space might be the air cleanliness, classification and monitoring. It might have supplementary cleanliness requirements like microbiological cleanliness, nanoscale particles, particles on surfaces, and so on. So I would have to, the user would have to define those. The designer would have to be aware of those. Also, there are likely to be temperature and humidity requirements for comfort and product related. And then there's some dynamic things that are defined in the regulations, like recovery time, which is all to do with ventilation effectiveness, and room pressure differentials. They are defined in the regulations. So you have to take those and apply them, engineer a solution, commission and demonstrate that it works. Now, some of the things that we need to engineer, so the critical operational parameters, are things like non-unidirectional airflow volume. We need enough clean air to maintain the conditions. If it's unidirectional airflow, we need to control the velocity and uniformity. Uniformity by smoke patterns. Room pressure control is critical, just as in containment laboratories. Room pressure is the most difficult attribute to control, I promise you. It's the one that goes wrong most often. We have to do and manage all the psychrometric performance. It's just like any close controlled air conditioning system. And ventilation effectiveness has become really critical recently, particularly as we've focused on energy saving and making sure our clean air is delivered and mixes well to minimize air quantities. I'll talk a little bit more about that in a moment. So the heart of the matter are the performance attributes mandated in regulations, and these are all monitored in real time and assessed by an authority who is approving the products to go to market. Continuous measurement of those. And most of the other ones are engineering parameters that the engineering department has to be right on top of from the building automation system, for example. So beyond commissioning, there is a set of regulations we work to, which happens to be GMP Annex 15, which is called qualification and validation. Here, there is a well-proven set of mandatory steps in the process of designing, installing, commissioning, starting up, and providing evidence that it works. And we call these qualification stages. So it starts off with the user requirements. These are not Mickey Mouse user requirements. These are real nuts and bolts, detailed requirements that characterize the needs of the space. Design qualification is a proper, aggressive design review where you pick the design apart to make sure that all those quality attributes are achievable. And I would interrogate a system to find out what the designer's intent was for the room pressure control. It's an expert task. It's not just tick box bullshit stuff. It's an expert task of evaluating and scrutinizing the design. It is cheap on paper. It's expensive when it goes wrong in reality. Then with installation qualification is making sure that the components that are installed were as per the design. Then we get into performance, qualification, operational qualification, and ultimately process validation. Then there is specialized activity related to computer systems, and for the processes, special activities related to cleaning and reusing equipment. So a lot of equipment, stainless steel equipment, is used for multiple products, and you've got to be assured you've removed the residue of the preceding products. So there's this whole philosophy that you would have to follow in the design and build of a capital project meeting these regulations. So be clear about the terminology. So we validate processes. So the manufacturing process, and this will be an end user responsibility, they will have to carry out validation to demonstrate they can fill vials like this consistently and deliver them sterile to the customer. We wouldn't get involved in that activity unless we were involved in some aspect of the process delivery. Now, that unit is filled on qualified equipment. So we would be involved in the engineering of this machine or its integration into the facility, and there would be an activity beyond commissioning to qualify its performance. And that equipment would then sit in a qualified facility. So it might be in the clean room with background performance, and that again is commissioned and qualified. And it will have a whole lot of mission critical utilities. So water systems of high purity, gas systems, compressed air systems, and so on. So, and all those would come under the remit of an expert building services team. Quite often vendor design involved, but the vendor needs to be controlled. So good engineering practice. So this is a message I always send out. No amount of qualification and validation will fix a badly executed project. If the engineering was bad, the install was bad, the commissioning wasn't done, you will end up in the end discovering the problem late in the day and spending a lot of money to sort it out. So the technical foundation is good engineering practice and good commissioning practice. And CIBSE has guidelines on that. Commissioning codes from BSRIA and NEB are critical to the commissioning part. Good engineering practice in the pharmaceutical industry is best codified in an ISPE, International Society for Pharmaceutical Engineering guideline. So good engineering practice, that is a guideline that is certainly all customers, end users should have that when they're looking at procuring external skills, and any engineering firm that is delivering into this sector should be aware of this kind of guidance. And I would say it would equally apply to biocontainment and so on. So it's established engineering methods. There's nothing special here. It's sort of common sense, but it's all around having competent, experienced people. So design and installation incorporating safety, health, environmental, ergonomic, economic, and so on. Professional and competent project management, engineering design, procurement, construction, installation, commissioning, and maintenance. All critical, and they need to have a degree of expertise, for these systems are more complex and more mission critical. Documentation. If it's not well documented, it's just a dream, is what we say. It has to be good documentation, and it has to be kept up to date through the life cycle of the project and the life cycle of the facility. So if you do modifications, you need to keep it all up to date. We have a V model here that is used classically. We start off with the user requirements. We go through the functional design, detailed design, implement the project, and then we go up the checks and balances. So we have that Annex 15 qualification steps that go up here. And today we try and integrate commissioning into this so that we avoid getting somebody to balance the HVAC and measure the air volumes and pressures, and then pay another bunch of people to measure the same thing. We would take the evidence from the commissioning engineer, provided they were competent, had properly calibrated instruments, and there was oversight and counter signature on the readings that they take. Just some examples. So design qualification. So inside one of these isolated devices, it would now be very, very common to use computational fluid dynamics to prove and sort out on paper or in computer the airflow in this critical space. The last thing we want is to get to doing visualization, which we'd have to do with smoke patterns in the final analysis, and find it doesn't work. So our regulators would not accept a CFD study as the only evidence of satisfactory performance. They would, in addition, we would have to carry out testing to demonstrate that that clean zone is working effectively with airflow visualization and measuring the cleanliness attributes, the particles, the microbiological cleanliness, so on. We have to provide ongoing evidence that we are in control. So our systems need to have attributes in them that allow that to happen. So continuous and frequent or periodic measurement of those critical attributes will be built into the clean room or clean air device. We need to differentiate those critical parameters that require a QA, quality assurance, oversight. This is the organization in a drug company that approves the medicine for release to the customers, to the patients, from the engineering stuff that also requires oversight, but only at an engineering level. So we're really in control, for example, of pressure drop across pre-filters. We don't want to have a surprise that the filter suddenly gets bunged up. So we're perhaps looking at rate of fouling of filters so we can predict end quality. So critical parameters require qualification, and the engineering parameters, maybe taking the evidence from a building automation system, need good, best engineering practices. So we try and differentiate to reduce the burden on the quality assurance professionals in the business. It means the engineering team running the plant need to be pretty switched on and higher level of competence than needed in most office blocks and hotels. Okay, finally, sustainability. So we've seen lots of this, melting stuff, flooded stuff, and on fire stuff. We mustn't forget sustainability. In our clean room type environments, 50 to 80%, depending on the site, of the energy is used in HVAC systems and their associated cooling, for example. So mostly fan power, heating and cooling. Sankey diagrams are great for looking at that energy balance, and the electricity bit, national grid and the power generators are going to solve that. That'll all be low or net zero carbon. Getting rid of the burning stuff, the gas, as Carl's already mentioned, is really much more difficult. We can do things to reduce the energy consumption of our HVAC systems, make them more efficient, convert to electrically powered systems, but processes are much, much more difficult. There are lots of projects going on at the moment in the life science sector, retro-engineering existing systems to reduce the energy consumption. There are standards related to this, particularly clean room related. So there's lots out there to help us. So you've got ISO 50001 energy management systems. So it's just like ISO 9001. It doesn't actually, it's not prescriptive. It's just saying your business, your organization needs to be tooled up to manage energy. In the clean room arena, there's part 19 of this family of standards. It's called Energy Efficiency in Clean Rooms and Separative Devices. This was written first as a British standard, and then we morphed it into an ISO standard. So we've got professional engineers who've been heavily involved. Am I all right for time?
Yeah, we've got 2 minutes left. Yeah.
Okay. Then there's part 4 of the clean room standards that's recently been updated. Design, construction and startup of clean rooms are really important to clean room designers. And it has a logical sequence of design of clean rooms from URS to commissioning and startup. And it has a whole lot of things in it about energy reduction at the design or at the re-engineering stage. And it avoids things like over-design. Because we all want to be safe, don't we? So we all tuck 10% spare in our back pockets. And one of the key things here is it requires that all the overages, all the allowances that are made are openly declared. And that you know how much has been added to be sure, and that you avoid hidden reserves and you design the system to allow it to be tuned. Okay, so after 6 months, when I've got real evidence of cleanliness, microbiological levels, I actually find I don't need as much clean air and I can turn the system down. But I engineer that capability into it at the outset. So just an example of sustainability and energy practice in part 4. Part 16 has a big list of things to consider in clean room design when thinking about energy saving, energy reduction, which can be applied to a new design and also to a legacy system that you want to reverse engineer to reduce energy consumption. ISPE, I mentioned this organisation has a sustainable practice working group and has produced a whole lot of guidance on this whole book, $270 worth of book on HVAC system design for pharmaceutical applications. Clean room opportunities, new and existing. So some of the things we're doing, this is actively happening as we speak. So supply air volume based on need, no arbitrary 20 air changes per hour. To actually assess the source strength of contamination and to put in enough clean air to deal with the heat gain and the source strength of contamination. It's more difficult to do than sticking a finger in there and having a rule of thumb figure. Lowest cleanliness gain growth possible, so don't over-engineer. Make sure you've got a grip of the heat gains and remove heat sources at source rather than let them become a room load. Contamination, source strength, and ventilation effectiveness. Make sure that we're getting the best bang for the pound out of the air we're delivering to the clean room. So we're thinking about recovery times, ventilation effectiveness. Isolators have a big advantage in shrinking our critical zone. Operational control, so silent hour setback. So very common and typical, because the clean room is not working in anger for big chunks of time. So set the air volume back, maintain the pressure differences. And now some really interesting active control. This is VAV, based on a combination of measuring cleanliness in real time, as well as maybe temperature and relative humidity conditions, and varying the supply air volume based on demand. Now, I promise you, room pressure control gets 10 times more difficult when you have variable volume systems. So you need to think really carefully about it. Low pressure drop design. So this is systems designed with oversized filters and ducts and so on, so the static pressure losses in the system are reduced. So it has a capital cost impact, but a big energy reduction source. Okay, and then don't forget the black stuff, as I say, the black utilities as well, because they are a major part of our energy consumption. So this is a geothermal energy solution for a big pharmaceutical company, Janssen in Belgium, part of the Johnson & Johnson Group. Now, I'm particularly proud of this because my son is a geotechnical engineer. His company in Germany has engineered this system. So they're drilling for heat. So the well is nearly 2,500 meters deep. Now, this is serious drilling, right? This is oil well technology. So when all the oil well drilling stops, maybe, then you can divert the skills. It's transferable skills to drilling for heat. They're looking for water at 85 or higher from that well. They have a 2.7 kilometre heat network that runs around the site. Some of that heat is used directly for the low temperature requirements, and their objective is to save 30 to 40% of their carbon burning, their gas-fired steam boilers and so on. They use Siemens high temperature heat pumps to raise the temperature from 80 or 90 up to 150, so I can get up to sterilizing temperatures. And this technology is well proven. It's used in district heating systems in Germany, particularly in the southern bits in Bavaria. Very common there. So it is possible to do it. But I promise you, this is seriously expensive. So this company has spent something just approaching 20 million euros on re-engineering their energy source. It's a wealthy company and they can justify doing that. And they already source, apparently, their electricity comes from North Sea wind when the wind's blowing. Like ours, yesterday, we had a 65% wind. Do you look at the national grid?
I've got the app.
You got the app, good man. Wake up in the morning and decide whether it's a good day or a bad day, whether you can turn the lights. Okay, so I've tried to cover a lot of ground about clean rooms, what they are. So it's keeping stuff out. The technology is very similar to cars, keeping stuff in. Different set of rules, but we use the same things. We use the same HEPA filters. We have to install them correctly. We have to leak test them and so on. And we need competent engineers to deliver at all steps of the process. The concept, detailed engineering, implementation, commissioning, startup, and then adding on these special things for qualifying GMP systems. Thanks very much.
There's a few more minutes. I'm just going to try and get onto the see if we've got any questions actually onto the teams going for that way. If not, have we got any questions actually into the room that actually want to ask the two fantastic speakers? No. Go on.
About the isolators.
Yes.
Are they actually basically in a qualified clean room already to make sure that they work as a clean room?
So they depending what the process is internally, they are usually required to be in a clean room as well, a background environment.
So I've got some questions as well. I wasn't just my phone being rude.
That's okay.
What do you feel is the biggest risk? Effectively, London especially is seeing a large increase in life sciences in that way. What do you feel was something for people to consider actually around that sort of point? I know there's lots of it come up around. You've got the crick. It's not from far bit here. What do you feel is the biggest thing we've got to worry about?
Personally, I think that for built up areas, London, I would have said there would be a limit to the sort of containment levels that we could go to safely.
Yeah.
Containment level 3, most should be blind and working on, built up community space. Anything beyond that, you really need to take that step.
Make it outside. Yep, fine.
Which is why Portland Down is in the middle of Salisbury Plain, surrounded by Salisbury.
Yeah, you got nothing. Yeah, exactly. Expendable. I've got a question for you, Gordon, here actually from the teams. What are the most common mistakes that you have encountered?
Okay, so I would say the number one parameter that goes out most commonly is room pressure.
Yeah.
So I would say pressure control, pressure balancing, and understanding how to achieve that. If I had to choose one, I would say that. And the other thing is that over design. In the days when we weren't really fussed about energy consumption,
Yep.
we could just throw 30 air changes and
Covered then, aren't you?
covered.
Yeah, yeah.
And I promise you that if you start to push it tighter and tighter and tighter to the edge of failure, as a designer, you're taking more responsibility.
Well, what's more important then is your life. That's always the question.
Well,
Isn't
that's
it?
that. Yes. Yeah.
Yeah.
Yeah. Or saving the planet.
Yeah.
You know?
Yeah, exactly.
Or your professional indemnity.
Right, insurance companies. Probably a question then for both of you. I've got skill set. Obviously, the UK is already acknowledged and probably worldwide over the skills gap. Are you seeing that? Obviously, in your positions, you've got the maybe the industry's not coming through. There's a big focus more around on the commercial side going for that way, or the energy management on the fluffy sort of stuff. And are you seeing enough people coming through, into this sector that's going to make sure it's supported? Because COVID sort of highlighted the concern we've got with the need for having that development. And you've got the big point. Do you think the skills are there, and they're being taught right?
What I'm seeing, skills not there. The reason I say that is that many occasions we're actually asking skilled people to stay on,
To upskill.
time and pay
Right. Okay.
to keep those skills going and put them back into the industry.
Oh, that's good. Let's
So I think there are some skills there, maybe not enough. I think it's often more to do with the way the projects are procured. So sadly, I get involved in expert opinion on ones that have gone wrong.
At the ends, when it's more profitable, right?
Yes.
Yep.
And often that is, first of all, the user requirements weren't defined because the users are not technically expert.
Yep.
Okay. So they need to recognise that and hire the right people to define the requirements. And usually that isn't done.
But is that down to the client not bringing them in, or the people they brought in aren't almost confident to go for the right
way around? So it's choosing the wrong people.
Yeah.
Then I would say there's an obsession with project management just following the procurement rules, not actually getting a grip of the competence of the designers and doing the checks and balances as the design develops.
So do you feel that's more related to where they feel they're interposable skills? So between a commercial development, you're using the same
I think it's
skill to transfer over to a life
I
science?
see very often that in the health service particularly, clean room procured via design build route,
Has room for
a
improvement.
very limited URS thrown over the fence to a design and build contractor and they've gone out to 5 and they're trying to put in a fixed price bid without doing any work.
Yeah.
All finger in the air guess and what I did last time. And then they get the job and then,
I missed out for chiller.
and then they start to have to find corners. Then it all goes wrong.
Yes.
Or they put the B team on it because they're cheaper.
Yeah.
So that's a problem. But if you were to move to the heavier end, so the young lady there works for Jacobs. So if you go to a big firm like Jacobs, they have a lot of expertise in the life science sector, but they would charge you serious money to write the requirements and do a conceptual design before you ever start getting into detailed design and going out to tender. So I think there's a real problem in not recognizing that these complex facilities need a different level of engineering detail.
Is it, do you reckon it's that, or obviously it is needed due to complex aspects? Do you feel there's almost the same processes trying to be followed as a commercial development actually moved over, where actually you can't take the traditional route of stage 3 procure going for that way? Should actually almost the stage 4 be done earlier on,
so
and
I think,
allowed actually for the costing to be done,
so
designed to be more accurately?
So I think the office block and hotel procurement route doesn't work.
Correct.
If I can phrase it like that.
I was looking back on the project management element. I do think there's an issue with project management of industry.
Sorry, are you feeling that it's construction wide, or are you saying it's more around the life science critical environments?
I would say it's probably construction wide, but when it's applied
Yep.
to a critical system, I'm actually qualified registered project manager. I only do so after becoming qualified
To fill the
engineer,
gap,
as an engineer, to make sure that when you actually want to manage a project, it's not just about the process, you need to have enough knowledge and how you actually manage it.
Yep.
And what you actually applying it to. I see too many project managers who are just following process rather than actually understanding what it is that they're trying to achieve as an objective project itself.
Because obviously, really, to be a good project manager, you've got to understand the point, and get the commercial development to be plus or minus 23 is an awful lot different from a 10,000 clean.
But understand what's critical.
Yes. Under the BE side
and
as
make
well,
sure
yeah.
it's scrutinized.
Yeah.
That's really important.
So obviously, unfortunately, with today's nature, BE is something that's got to happen. You've got to understand where that value engineering.
Nothing wrong with that.
Exactly, and it has to happen to a degree, but also I think sometimes where the skills come in, you've got to understand where you can deliver.
That's where it goes wrong.
But that exactly it is where people are actually trying to going for the wrong point, and there are ways of going around it differently, but you understand where the risk comes into it, where you can't necessarily go for a smaller ductwork, or you can't do it in the wrong way.
Well, you've got to make. There's nothing wrong with a process that challenges the value of the solution. Where it goes wrong is when you accept something that drops or reduces the performance of a critical element.
Yeah.
Right?
Yeah. No, I agree. We've got one more here. What the main changes in the latest version of you'll probably know off the top of your heads. It's 14644.4 compared to the previous version.
Okay, so ISO 14644 Part 4 is design, construction and startup. So it's more rigorous in taking you through all the steps from user requirements through to the design and commissioning. So it is more rigorous. It introduces into it greater clarity about defining the requirements. And the other major bit in it is that it's got more in it about sustainability and the questions you should ask during that critical part of the design when you have a chance to influence that before it gets too late. And it links into all these checks and balances. So design review, installation, ensuring what is installed is actually what was designed. It's actually moving back, to the 40 years ago, we had people on site who were scrutinizing the quality of the install. Clerks of work, they used to be called. And now we tend to be much more dependent on the vendors or the contractors.
Self-marking your homework shouldn't really be that. Yeah. No, which is great to hear. It does sound like actually that's almost what should be implied as a standard across the whole construction industry, rather than actually related to clean rooms. I've got one more actually on the team. Anything from the audience so far? No. Okay. From experience, after fine tuning on site, what would be the adequate ACH to achieve different class of clean room?
What's necessary?
what would be adequate? What would be the adequate ACH to achieve different class?
So we're trying to move away from that. The whole thing is to move away from rules of thumb.
Yep.
And actually make the design appropriate to the contamination source strength in the space.
So do you feel that actually there may be, you know, the BIM and the detailed modelling and that sort of stuff would actually help that way more, or?
It's not likely to be the BIM, it's more likely to be CFD, computational.
The more detailed
More detailed
aspect.
design.
Obviously,
Yes.
the reason why I sort of mentioned BIM, it all tries to put the information model going for the whole way, trying to bring the whole lot.
Okay, but this is
together.
before you put the model together. This is actually the basis of the design. So
Yeah.
that I'm working out how much clean air I need in this space to satisfy the heat gains, for example, as well as the cleanliness levels based on the source of contamination in the space. Now, there are some rules of thumb which experienced people would use as a stopgap, and if I saw numbers dropping below a certain level, I would smell a rat. And if I was auditing your design, I would challenge you.
I'm sure mine would be good.
I would challenge you. I would challenge you on how you got there.
Yeah,
Right.
You
And I'd want to look at the maths.
Yep.
Right.
No, and that's the way that it should go.
It is more difficult, and the designer takes more responsibility as you fly closer and closer to the edge of failure. If you
Yes.
like, be aware of that. And which is why the Part 4 standard has this bit about, and the Part 16 standard I mentioned, being aware of the reserve you've built into your design and making sure it's tunable so you can turn down the width when you get evidence of the cleanliness. So I could build in, because I promise you, I'm not about to, if you are my client, I'm not going to take a big risk. There will be some allowance for the unknown.
Yes, yeah.
Whether it's heat gains or source strength contamination. But the standard is saying this should be openly declared. So
which actually I fully agree with. I think that should be
not
construction
not hidden secret.
which is often too much the case. I think there's some most lessons learned. We've got a question from the audience.
About sustainability.
Yes.
So commercial sector have certain accreditations, electric neighbours that drive sustainability on building owners' point of view. Is there what's actually driving sustainability?
So an end user can go for LEED, the US one, or BREEAM, something like that. For some of the facilities, the model doesn't generally fit terribly well for containment labs and clean rooms.
Is there anything in development?
So ISPE has some guidance, and slowly it's bringing out some, I would say, some performance metrics. So specific fan power. Okay, so if you're going to choose a fan, you should have fans with certain efficiency, effectively, or specific fan power. Starting to develop some rules of thumb on typical energy density that was mentioned in your talk.
The transfer of risk, though, isn't it? You try and drive it to sustainable and the mind ability to system work safely.
Yes, of course.
It's weighing up the priorities. So I think you're right. In a traditional built environment, there are some sacrifices you can make to comfort to get in a more sustainable area. But when you're talking life, energy's always got to be the second. But it doesn't mean the fact that straight away you mentioned these two numbers. I think actually it was you, Cole. They're 800 to 1,000. Straight away you start getting the 1,200, then you feel actually you've got means to start investigating as it sits, rather than the ability to almost hide behind it. It's almost got to be the second priority over the condition to be met. Is actually for the energy's got to sit, but never the first.
Biosafety trumps sustainability.
Yes, yeah.
Although you can add in total heat wheels after the filtration on a biosafety application.
Yep.
So I've done a lot of that, animal accommodation particularly, other runaround coils. And then if you're looking purely at veteran pathogens, animal pathogens, you're more concerned about stuff getting out. It's not a threat to the scientists in space. So actually you can use recirculation. And you might have an all outside air mode for fumigation, biodecontamination, for example. So there are all sorts of things you can engineer into a system. You know, containment laboratories, I mean, I would say normal practice to have systems that go to a silent hour setback. So I can maintain that pressure differential in that space with very, very low air turnover. And if the lab's silent, I don't need that air turnover, unless it's full of animals. Then, of course, research animals have a different demand. But interestingly, research animals are diminishing because we're now starting to do more and more in tissue culture.
I thought you were going to say children, but yes, it was sorry.
Or students.
Yeah, exactly. Do universities, that's fine.
But there are now companies growing human cell lines as tissue, which can be used in regenerative medicine, but also you can test cosmetics on it instead of doing it on nude mice or rabbits or dogs. Sorry, missed that. You can, yes. Well, you can if it's a last resort. Still, because there are some things that you cannot test on. You have to be in an animal model. I
So
promise you that's the case.
unfortunately, we have actually run out of time. We've gone over a little bit over, but I think it's been very worthwhile. Some really positive feedback actually coming from the site here. If we just give a one last round of applause for the three fantastic speakers here. Really thank you for your time. Appreciate it. And Wednesday evening. Unfortunately, I think we're only got about 10 more minutes before we actually got to get out the points, the things that come in. But I think that really, again, hopefully get some really positive feedback. I know the numbers haven't been as good as what we've gone to, but if we can try and get some things come back either linked in that way, we'll try and make sure that CIBSE consider this as a bigger consideration to take forwards as it sits. It's not sort of sustainably driven, but from the HVAC group, it's really a key subject that's got to be picked up and the knowledge has got to be shared. So one last time, thank you for the speakers again. Really appreciate your time. Thank you very much.